Hello dear students, I am Praveen, your chemistry educator. Students, in this video, in this session, what we are going to do, we are going to cover the full chemical kinetics chapter from your 12th class, right? And I hope if you are solving the previous year questions, so you already know that from this chemical kinetics chapter, we get at least 2 questions in the NEET examination, right? And those 2 questions, right, if you are mathematically strong in this chapter, you can easily solve. So in this video, of course, I will be covering each and every topic. But you know very well, if you have studied this once, that this chapter is a little bit mathematical, right? So in those mathematical parts, right, I will help you, I will make it very easy for you to understand. Believe me, after this session, you will be able to solve each and every question in this chapter, like whether it is from Arrhenius equation, or it is from integrated rate law, or it is from simple rate law. You need to focus in this session, in this video. And of course, after watching this video, after completing this session, now it is your task to practice questions, practice problems. And from where you can practice the questions, we are providing it, right? We are providing the DPPs in the description of the video, and also download the PW app. And on the PW app also, you can get these DPPs of chemical kinetics as well as for the other chapters, right? And for the other subjects. So now students, first let's see that in today's session, what are the topics that we will be covering in the chemical kinetics chapter, right? So first of all, we will see what is rate of reaction, like what is the meaning of rate, what is the meaning of rate of chemical reaction. Then we will talk about the types of rate, right? We have average and instantaneous rates. So we will understand what is the meaning of average and instantaneous rate. Then we will talk about the most famous topic of this chapter, that is rate law, followed by we will discuss rate constant and its units, like how units are different for rate constant. And then we will talk about what is order of reaction, and then we will discuss what is the difference between elementary and complex reaction. So we have elementary and complex reaction, and we will see that what are the differences between elementary and complex reaction is there. Then we will see how we can calculate order in a complex reaction. So if it is a complex reaction, how for a complex reaction we can calculate the order. And then we will talk about the difference between order and molecularity. Definitely orders and molecularities are different terms. So we will have to see the differences, the main differences between order and molecularity. And then we will talk about the most, you can say, famous, important for your examination, that is integrated rate law. And in the integrated rate law only, we have another part that is called half-life, and we have then pseudo first order reaction. So we'll understand what is the meaning of pseudo first order reaction, what are the examples of a pseudo first order reaction, and then we will talk about how temperature affects rate of a chemical reaction. Then Arrhenius equation. Arrhenius equation also tells you that how temperature is related with your rate or rate constant. And then the meaning of activation energy. We have certain graphs of activation energy, their applications. We get questions from the graphs of activation energy. So we have to understand in detail about regarding the graphs of activation energy. Then we will talk about effect of catalyst on rate of reaction. And then finally, we will end this chapter with the concept of collision theory. So now, without wasting any time, let's start with the very first topic, that is rate. Students, before I talk about what is rate of reaction, you need to understand what is the meaning of rate. I hope you know from your physics also that rate is something with respect to time. Like whenever there is a parameter and that parameter is compared with respect to time, the parameter's change is compared with respect to time, so that is called as rate. For example, you have always said that velocity, right? Velocity is what? Velocity is change in displacement with respect to change in time. So point is, velocity is a rate because velocity is calculated by calculating change in displacement divided by change in time. So like this, you take anything, any parameter, its change if you compare with respect to time, so that thing is called as rate. Now similarly, when you say that rate of chemical reaction, so in that we have to take certain parameters from the reaction and their change we have to compare with respect to time. And the most common parameter in reaction is concentration, molarity, right? Like suppose that a reaction is happening, something like this. N2 plus 3H2 gives you twice of NH3. So in chemical kinetics, it is also important to understand that how a reaction occurs, how a reaction happens. So suppose if this is a reaction, chemical equation in which N2H2 are your reactants and NH3 is your product. So how this reaction will happen? Initially by default, you will have certain amount of reactants, and if it is not mentioned, by default the amount of product we take as 0. Now suppose here that initially the concentration of N2 I took, I'm just taking an example, right, from my side. The concentration of N2 initially it was 20 molar, and the concentration of H2 initially it was 40 molar, and initially there were no products, so concentration of ammonia will be 0. Now how this reaction will happen? You know that as time passes, the concentration, the amount of reactant, it will decrease. With time, the amount of reactant will decrease because reactants will convert into product. So with time, concentration or amount of reactant will decrease. At the same time, the concentration or amount of product will increase. And students, you know that it is a general point, right? You take any reaction, if it is happening in the forward direction, so with time, if reaction is happening, the concentration or amount of reactant will definitely decrease, and the concentration or amount of product will definitely increase. Now suppose I started this reaction initially at t equals to 0 second, Now after 10 seconds, some of the reactants will react. So let me assume something. Let us say that in 10 seconds, 3 molar, I am saying that in 10 seconds, 3 molar of N2 is reacting. So if 3 molar of N2 will react in 10 seconds and initially it is 20 molar, so how much it will remain? Initially it was 20 and in 10 seconds 3 molar is reacting, so it will remain how much? 17 molar. And I hope you all know stoichiometry very well, class 11th first chapter. According to stoichiometry here, if I see, so 1 mole of N2 will completely react with 3 moles of H2. So that means what? If 3 molar of N2 is reacting, so it will react with 9 molar with H2, 9 molars of H2. And now H2 initially I took 40 molar and its 9 molar is reacting, so how much it will remain? It will remain 40 minus 9, that means 31 molar. And in the same way, you can also calculate that how much product will be formed here, because one part of N2 can form 2 parts of NH3. So if 3 molar N2 is reacting, it will create 3 into 2, that means 6 molars of NH3. And if 6 molar of NH3 is getting formed, and initially it is 0, so after 10 seconds, the molarity of NH3 will be 6 molar. So like this, the reaction will proceed, right? After 20 seconds, more N2H2 will react, more NH3 will be formed, and so on, right? But point is, we have to understand rate here. And rate of chemical reaction, right, very commonly calculated with respect to concentration. But it's not mandatory. Please try to understand. We use concentration most of the time, but rate of a reaction can be calculated with help of change in pressure, change in mole, change in number of particles, change in volume, right? Similarly, change in concentration. So change in pressure, change in mole, change in volume, change in concentration with respect to time when you do, so that is called rate of reaction. Now in this case, if I have to calculate rate of reaction, I will have to observe that how much N2 is changing, 3 molar, in how much time? 10 seconds, right? So if I do change in concentration of N2, which is 3, divided by change in time, which is 10, so 3 by 10 will give you the rate. But a very important point is here. Students, in this chapter, we start with rate. First, we try to understand like what is rate of reaction. And I hope that till now you have understood one thing, that in chemical kinetics, rate commonly calculated as change in concentration of reactant or product divided by change in time or time taken. But we have 3 types of rate here. And that's the first point you need to notice, you need to focus here. We have 3 types of rate, right? One is rate of appearance, one is rate of appearance, the other one is rate of disappearance, right? And the third one is rate of reaction. The third one is rate of reaction. And I hope that this is clear from the name itself. When you say rate of appearance, so rate of appearance is applicable for the products. For the products. Rate of appearance means that by which rate your products are getting formed, right? So the rate by which products are getting formed, it is called as rate of appearance. Similarly, the rate of disappearance, it is for your reactants, right? You know that during the course of reaction, during the course of forward reaction, the reactant will decrease. So the rate by which the reactants are decreasing, so that is called as rate of disappearance. That is called as rate of disappearance. And then for a reaction, overall if you calculate a rate, for the whole reaction, not specifically for the reactant or product, for the overall reaction. So for overall reaction, you call it as rate of reaction. And not only that, we have a relation. We have a relation between rate of appearance, disappearance with rate of reaction. And let's try to understand that first. Like in this example, if you notice, for N2H2, if I calculate the rate, right, that will be called as rate of disappearance, right? I can say that here, rate of disappearance, ROD means rate of disappearance of N2, if I calculate that, so for N2 you notice in 10 seconds, it is changing by 3 molar. So for N2, the rate of disappearance will be change in molarity, which is 3, divided by change in time, which is 10, so it will be 0.3. So 0.3 molar per second is the rate of disappearance of N2 here. In the same way, I can also calculate rate of disappearance of hydrogen, because hydrogen is also your reactant, right? And for hydrogen, if I see, in 10 seconds, it is changing by 9 molar. It is changing by 9 molar. So for hydrogen, the rate of disappearance will be change in concentration, which is 9, divided by change in time, which is 10. So it will be 0.9 molar per second, right? So for reactants, we call it rate of disappearance. But for products, we call it rate of appearance. Like for NH3, I will call it ROA, in short, rate of appearance. And if I calculate here the rate of appearance of NH3, so rate of appearance of NH3 will be change in the concentration of ammonia, which is 6 molar, divided by change in time, which I took 10 seconds. So 6 by 10, it will be 0.6 molar per second. So for this example, for this particular reaction, rate of disappearance of N2, rate of disappearance of H2, rate of appearance of NH3, we calculated. In the same way, if you have the data, that how much your reactant or product is changing in how much time, so you can also calculate rate of disappearance or appearance for any chemical reaction in the same way. Change in concentration divided by time taken, right? Now, point is, from this rate of disappearance or appearance, we can calculate the overall rate of reaction. Students, the overall rate of reaction in any case can be calculated as rate of appearance or rate of disappearance divided by stoichiometric coefficient. So point is, once you have calculated rate of appearance and disappearance, if you divide that by the corresponding stoichiometric coefficient, and that you can get from the equation. So by dividing with a stoichiometric coefficient, you can find your rate of reaction. And why we divide with a stoichiometric coefficient? Because when you divide with a stoichiometric coefficient, the rate is calculated per mole, right? And if you do that, every time you will get the same value. Like here you notice that rate of disappearance of N2 is 0.3, rate of disappearance of H2 is 0.9. So these two are different values, right? So if you have to find out the rate of reaction, you cannot say directly that rate of disappearance is rate of reaction, or you cannot say directly that rate of disappearance of H2 is rate of reaction, because these two are different values, right? But when you divide that by stoichiometric coefficient, every time you get same value. Like suppose in this case, in this example, if I have to calculate rate of reaction and I do that from N2. So for N2 rate of disappearance is 0.3 and for N2 the coefficient is 1. So 0.3 by 1 from N2 the rate of reaction will become 0.3, right? The same thing if I calculate from hydrogen. So for hydrogen the rate of disappearance is 0.9, right? And for hydrogen the coefficient is 3. So if I divide rate of disappearance 0.9 by coefficient 3, so 0.9 by 3 will become how much? 0.3. So from here also you will get 0.3. And if you calculate the same with NH3, right? So for NH3 the rate of appearance is 0.6 and its coefficient is 2. So rate of appearance 0.6 by 2, it will also give you 0.3. So when you divide rate of appearance disappearance by stoichiometric coefficient, you get a same value, unique value every time. And that's why this particular term, rate of appearance disappearance divided by stoichiometric coefficient or rate of appearance per mole, rate of disappearance per mole, that term we have defined as overall rate of reaction, right? And from this also you get question in the NEET examination. You get questions from this, like what type of questions you will be getting from here. They will give you rate of appearance of one of the product and they can ask what is the rate of disappearance of any of the reactant. So what you have to do, from the appearance and disappearance, divide with a stoichiometric coefficient. Now both are rate, just equate them. Just by equating, you will get your answers, right? But I hope that now you all have understood very well that what is the meaning of rate. Rate means change of any parameter with respect to time. And in our chapter chemical kinetics, for reactions, we take change in concentration with respect to change in time. And not only concentration, instead of concentration, you can consider change in pressure, moles, number of particles, volume and all, right? But the most important point is, now I think you have understood that what is rate of disappearance, right? The rate by which the concentration of reactants are changing, and you have also understood rate of appearance means the rate by which the concentration of products are changing. And if you divide this with a stoichiometric coefficient, so that gives you the overall rate of reaction, correct? So I hope that from this point, if you get a question, you people will definitely solve that, right? So moving forward, after understanding rate, now let's understand the classification of rate as average and instantaneous. So this is again very easy. Students, when you say average, right? So that means here rate is calculated in a larger range, in a larger interval of time. And when you say instantaneous, so that basically means that the range will be very small. The interval of time will be very small, tends to 0. Like here we have a graph. If you try to understand this, in this graph, on the y-axis we are plotting concentration. On the x-axis we have plotted what? Time. So with time, in a forward reaction, you know that concentration of reactant, it will decrease. So initially the reactant had certain value, certain concentration, and as time will pass, because your reactant will convert into product, so concentration of reactant with time it will decrease. But at the same time, the concentration of product, initially it was 0, but with time, as reaction proceeds, so concentration of product will increase. This is a general concept for every forward reaction, right? Now, point is, if I have to calculate average rate, what I will do, I will start, let us suppose from 20 seconds, and I will take till 40 seconds, right? So, I am doing this, you can do this with respect to reactant or product, anyone, because you know that from appearance, disappearance, both we can find the rate of reaction. So, I am doing this with product. Suppose that at 20 seconds, the concentration of product is R1, right? Or at 40 seconds, the concentration of product has become R2. So now if I take this interval, 20 to 40, right? And between 20 to 40, total 20 seconds is there, right? The interval is of 20 seconds, which is a large interval, right? So in this 20-second interval, if I find the change in concentration of product R2 minus R1 and I divide that by 20 seconds, total time taken, so that will give you average rate. So average rate is calculated in a large interval, 5 seconds, 1 second, 10 second, 20 second. But suppose if I take a very small interval, like I start from here and I end here, right? This is my interval. It will be even difficult to draw that much small interval, you know, very difficult to draw. But still I will try to do that. So you can notice that here the change is very small. The time interval is very small, almost tends to 0. So in this very small interval of time, if you calculate rate, right, so that you can get by the slope of the curve, But that small interval, if you calculate rate in that, so that is called as instantaneous rate. And not only that, we have a difference in representation. Right? Suppose from the product, if I calculate the rate, the average rate. So average rate can be written as delta, means change in concentration of product upon delta of T. So average rate is denoted in the chapter throughout by this delta. Delta although means larger change, right? In both physics, chemistry, in many chapters you may have seen that when we write delta, so delta indicates larger change. And when you write D, elemental change, right? So that is for instantaneous rate. If you talk about your instantaneous rate, so instantaneous rate is denoted for the same product, D of P divided by D of T. So when I write D of P, D of T, so that is also change in concentration of product, change in time, but for a very, very small range. Here you can say that this dt tends to 0. Not exactly 0, tends to 0. If dt tends to 0, that means what? We are taking a very, very small interval. But in this part, you need to know just the representation part. Just the representation, if you know, that is more than enough for you. You need to understand one thing only, that if it is written in terms of delta, it is average rate. And if it is written in terms of dp by dt, then it is your instantaneous rate. So now I think you have understood what is the meaning of average and instantaneous rates, right? So moving further, after instantaneous and average rate, now we have one of the most important topic of this chapter, students. And from this you get so many questions, so many times we have got questions. If you see PYQ, you will find it out. The topic is rate law. Okay, let me tell you one thing. The summary of this chapter once. Students, you understood rate, and rate of reaction tells you that how fast a reaction is going on, right? If the rate of a reaction is more, that means the reaction will complete in a very short span of time overall. And if the rate of reaction is very, very low, that means then your reaction will be very, very slow. So rate is directly connected with the speed of your reaction, right? How fast your reaction can occur, that is determined by the rate of reaction. But the point is, throughout the chapter, you will be discussing about how rate is affected. The whole chapter is based on that topic. The rate of reaction, in your 10th class also, I hope you must have studied somewhere that rate of reaction is affected by different parameters, right? Some of them are surface area of a reactant, temperature, concentration, catalyst, right? So all those factors you will be discussing in this chapter. And overall you can say that that's the syllabus of the chapter. Throughout the chapter, after understanding rate, we have to study that how rate is affected by different parameters, right? And out of all those parameters, one of the parameter is concentration of reactant, or more precisely, it's better to say active mass of the reactant, right? Now, how rate is connected, how rate is related with the concentration or active mass of reactant, right? That relation is nothing but your rate law. Rate law says that rate is directly proportional to the active mass or concentration of reactants, right? But here we have a point. No doubt rate of reaction is directly proportional to the concentration or active mass of reactant, right? But for each concentration terms, there will be some power value. Concentration term, and the concentration term will have some power value, right? And those power values are calculated only experimentally. So that point also we need to write down in the rate law, that rate is directly proportional to the concentration of reactants raised to the power some value which is calculated experimentally. Only using experiments you can find those power values, and those power values are only nothing but your order. Later on you are going to see that those power values, right, on the concentration terms, they are known as order. So let me give you an example here, right? Suppose that if I have a reaction in which A and B are the reactants, and by reacting it is giving you some product, right? Although we are not writing what products we are getting, because in rate law we do not talk about the concentration of product. But let me tell you one thing. In the rate law, we don't talk about the concentration of product, but that does not mean that rate will be independent of concentration of products. Just like the concentration of reactant, rate can also depend on the concentration of products as well, right? In so many reactions that will happen. But in rate law, we are strictly talking about only the reactant part. So A and B are your reactants, and by reacting, it is giving you some product. Now here, if I write down the rate law, I can say that the overall rate of reaction R is proportional to the concentration active mass of reactants. So concentration of A into concentration of B, all the reactants. Now these reactant terms, the concentration of the reactant terms, it will have some power values. Let's say that for A the power is X and for B the power is Y. So these power values, these X and Y, these are calculated only experimentally, and these are called orders. Here X is order with respect to A and Y is order with respect to B. And if you sum that, if you add that, so you can say that X plus Y is overall order of the reaction, overall order of the chemical reaction. But the main thing is, this is your rate law. Rate law says that rate is proportional to concentration of reactants raised to the power some value which is calculated experimentally, and it is known as order. Now you know that whenever we remove proportionality constant, so we put some constant here. So that constant here we will write it as K, and this K is nothing but called as rate constant. This K is called as rate constant. So rate equals to rate constant into concentration of A to the power X, concentration of B to the power Y. This will be the generalized rate law expression for this particular reaction. For this particular reaction which I took as example, A plus B gives product. And like this, you can write down rate laws of any of the chemical reaction. It will be concentration of reactants raised to the power order, right, which is calculated experimentally. And in the questions, right, sometimes if you find out that concentration of product or concentration of catalyst is written, so do not get confused by that. It is possible that rate can depend on concentration of product as well as concentration of catalyst, right? So in expressions, if you see that, do not get confused. Do not try to think that only reactants concentration will be there. In the rate expression, you can have concentration of product as well, right? So now after understanding rate law, that rate is proportional to concentration of reactant, let's focus on a little bit on the rate constant. Because you know what, For this rate constant, the unit will change with respect to order. As your order changes for different reaction, so with order, the rate constant's unit will also differ. Like suppose if I write a generalized equation that rate of reaction is equals to rate constant into concentration of reactant raised to the power n, where n is your order. So in this case, I have taken only one reactant. I have not taken multiple reactant. I have taken only one reactant, that is R, and n is your order. Now suppose for a reaction, if your order value is 0, if order value is 0, if n is 0, so in that case, the expression, the general expression can be written as rate is equals to rate constant into concentration of reactant power 0. Now you know very well that for any term, if I take power as 0, so that becomes 1. So from here I can say that rate is equals to rate constant. So from this I can say that for zero order reaction, the unit of rate constant will be exactly equals to the unit of rate. And generally we take a unit of rate as molarity per second, molarity per minute, molarity per hour. So that will be the unit of rate constant in case of zero order reaction. So in general I can say that for zero order reaction, the unit of rate constant will be molarity per second, or molarity can also be written as mole per liter. So mole per liter per second, right? Similarly, you can find out unit of rate constant for other orders also. Like if I take first order reaction. So for first order reaction, the power will be 1, and in that case, the expression, general expression can be written as rate is equals to rate constant into concentration of reactant to the power 1. Now in this case, you can see that rate constant will be rate upon the concentration of reactant. Now in this case, right, the unit of rate constant will be either per second, per minute or per hour, because the unit of concentration will be cancelled out here, right? In rate, you have concentration by time, and upon concentration, so unit of concentration will be cancelled out here. So in this case, the unit of rate constant will be per second, per minute or per hour, right? So there is no concentration term here. There is no unit of concentration in the unit of rate constant in the first order reaction. And I hope that in the same way, you can also find out the unit of rate constant for the second order. In that case, rate will be rate constant into concentration to the power 2. So from here, rate constant will be unit of rate divided by unit of concentration power 2. And I hope that you can easily find it out, right? So please find it out and write down that in the comment box. I will personally check that, right? Whether you are doing it right or wrong. But point is, for different orders, the unit of rate constant is different. And why I am discussing this point, right? One more reason is there, right? In the upcoming topics, you will notice that for solving the questions, you need to have knowledge of the order. And sometimes in your numerical questions, they will not mention that what is the order of reaction. In the numerical questions, they will give you the value of rate constant. And by looking at the value and unit of rate constant, especially the unit, so by looking at the unit of rate constant, you can easily figure it out what is the order of reaction, right? If the unit of rate constant is given something like per second, per minute, per hour, that means your reaction is of first order. If the unit of rate constant is given molarity per second, molarity per hour, molarity per minute, then definitely the order of your reaction is 0. So from unit of rate constant, you can easily find out what is the order of reaction. So now students, let's see a little bit of detail about the order of reaction. So we have already seen that in the rate law expression, right, when you write the expression of rate law, so the power of the concentration terms, right, they are known as order. But let's understand what can be the exact meaning of order, or what we can interpret from the order of reaction. So first of all, suppose that if you have a reaction whose rate law is something like we have rate constant into concentration of A to the power 1, concentration of B to the power 2. So if you have reaction something like this, whose rate law is this, rate constant into concentration of A power 1, concentration of B power 2. Then of course, in these types of rate law expression, you can easily find out what will be the order. Even you get questions like this also, like they will give you the rate law expression and you will have to say what is the order, and nothing to do, just add the power values, right? In this case, the power of A is 1 and the power of B is 2. So in this case, the overall order of reaction will be how much? It will be 3. But of course, from the rate law, we can easily find out the order from the expression. And the other thing is, by experiments, we can calculate what? Order. But what is the interpretation of order that we need to understand? Students, think like this. Think like this by referring into physics. Like in your physics, when you talk about motion in a straight line, right? Especially that chapter. So you have two types of motion. One is uniform motion, one is accelerated motion. So in uniform motion, what happens? The velocity remains constant. But when you talk about accelerated or retarded motion, so there the velocity changes with respect to time. The same interpretation, right? The concept of acceleration or retardation that you have in your physics, the similar type of concept you can relate, right, for order in your chemical kinetics chapter, right? What it means, as the order of reaction increases, right? So with that, the rate of reaction will also change and it will decrease with time. More the order, more the fluctuation we have in the rate of reaction overall with time. As you have a higher order reaction, so that means with time the rate of reaction will decrease that much rapidly. Like for example, if a reaction is there whose order is 0, so if a reaction is there whose order is 0, that means what? In this case, the rate will remain constant throughout the course of reaction, from the initial time to the final point of the reaction, right? From initial to final state of the reaction throughout, right? The rate of reaction will be constant if it is a 0 order reaction. But instead of 0 order, if you take a reaction having order 1, so in this case what will happen? Because your rate depends on concentration to the power 1. So with time, the concentration of reactant will decrease, and if the concentration of reactant will decrease, so with time the rate of reaction will also decrease. And here we have a linear relation, right? For order 1, with time you can say that rate of reaction will continuously decrease as the time passes, as the reaction proceeds, right? And the depreciation, the decrement will be more and more for higher order reaction. If you take a second order reaction, so in that case also, with time, as reaction proceeds, the rate will decrease, but the decrement will be more rapid as compared to first order. So kind of you can say like this, that in chemical kinetics, order is like a retardation. More the order, right, more rapidly the rate will decrease during the course of reaction from start, right? And one more thing you need to notice here, that for any reaction, right, at the initial state the rate is highest, right? If it is 0 order, the rate at initial state, the same will be there throughout the reaction. But for first and second order reaction, the rate is highest at the initial state, but as time passes, the rate of reaction will slowly decrease. So now I think at least you have understood what is the meaning and what is the interpretation of order with respect to reaction, right? Higher the order, more rapidly the rate will decrease with time during the course of reaction. Now, point is, after understanding in detail about order and rate law and rate constant, I hope that now you are pretty much comfortable in the rate law, right? Rate constant, its units, and what is order and what is the meaning of order. So now let's talk about a very interesting point. What is the meaning of elementary and complex reaction? It's a short point but important for the examination. Students, if you talk about different chemical reactions that we have in the organic part, in the inorganic part. So reactions, they can be classified into two parts, right? Some of the reactions, they will occur in single step, in one step, right? While there are many reactions which occurs not in single step but in multiple step. Multiple means two or more. Multiple means two or more. Single step means you have your reactant and your reactant is directly converting into your product, right? And multiple step means you have your reactant converts into some intermediate state, and then from that intermediate you get your products. Sometimes from one intermediate to another intermediate, right? Like that. So if a reaction is there which is happening in single step or one step, then it is called as elementary reaction. Then it is called as elementary reaction. But if a reaction is there which is happening in more than one step or multiple step, so those reactions we classify them as complex reaction. Those reactions are classified as complex reactions, and there are so many examples of elementary and complex reaction, but let me tell you some of the examples, especially from the organic chemistry. Like if you talk about organic chemistry, the alkyl halide chapter, so in alkyl halide you must have discussed regarding SN1 and SN2 reaction. SN1 is nucleophilic substitution, right, by first order, and SN2 is nucleophilic substitution by second order. So in that SN1 SN2, right, the SN2 reaction, the nucleophilic substitution reaction, right, which happens through SN2 mechanism, the SN2 reaction is a elementary or single step reaction because SN2 happens in one step. But at the same point, if you talk about the SN1 reaction, right, so SN1 mostly happens in two steps, but if it is two step, it is more than one step, right? So SN1 happens in two step. That means it is a multi-step reaction. So SN1 can be classified as complex reaction. And like that you have E1, E2 in the elimination part of organic in the same chapter alkyl halide, right? In that E1, E2 also, E2 is your elementary reaction while at the same time E1 is your complex reaction. So I think at least the meaning of these two you have understood. What is the meaning of elementary reaction and what is the meaning of complex reaction? Single step, elementary, and multi-step, that means complex. Now point is, in case of elementary reaction, like if you know that a reaction is there which is elementary, so in elementary reaction it is very easy to calculate the order, because what happens, students, in case of elementary reaction, in the balanced chemical equation, whatever stoichiometric coefficient is there, so that coefficient you can take as power in the rate law, and that can easily give you the order of reaction. So calculation of order is very easy if it is an elementary reaction. Suppose that I am telling you that we have a reaction like this, 2p plus q giving some product, okay, and until unless I don't tell you, you can't get that just by the equation. I will have to tell you that. So I am telling that this reaction is an elementary reaction. This is happening in one step. So if this is an elementary reaction, then for this, if I write rate law, I can write it like this: rate constant into concentration of the first reactant P power stoichiometric coefficient 2 into concentration of the second reactant Q power stoichiometric coefficient 1. So here the order will be 2 with respect to P and 1 with respect to Q. So overall order will be 2 plus 1, that means 3. So for elementary reaction, you can directly find out order if you have the balanced equation. But when you have a complex reaction, when you have a multi-step reaction, so in multi-step reaction, you have to learn how you can find the order. And from this very topic, you get direct questions in the NEET examination. Direct question. What type of questions they will give here? They will give you a reaction overall. They will give you the steps of the reaction because it is complex, and from those steps you will have to evaluate what is the order of reaction. So let me give you an example here. Suppose I have a reaction like this: A goes to B. This is the overall reaction, right? But I am saying that A goes to B, it is not a elementary reaction, it is a complex reaction. So if it is a complex reaction, definitely it will be happening in multiple steps. And now, apart from the overall reaction, I am also giving you the steps of this reaction, all these steps. So In the first step, what is happening here? The reactant A, it is converting into some compound P, right? Then in the second step, P is converting into some compound, let's say Q plus R, right? Not Q plus R, let's say just Q, keep it simple, just because we are understanding it. And in the third step, the Q is changing into B. So overall reaction is A to B, but it is happening in three different steps. In first step, A is changing into P, then in second, P is changing into Q, in third, Q is changing into B. Now, if I tell you that the first step here, it is slow, the second step is fast, and the third step is also fast, because this information is also required here, that which one is the faster step, which one is the slower step. So point is, out of all the steps in the mechanism, the slowest step is called as rate determining step. The slowest step is called as rate determining step, or in short we call it RDS. Now, why this slow step is called rate determining step? Because from the slow step, you write down the rate law expression, and whatever rate law expression you get from the slow step, that will be applicable for the overall reaction. So from the slower step, we can find the rate law of overall reaction. That is why it is called as rate determining step. Now here, I am not writing the rate law of this overall reaction. I am writing the rate law of the first step here, which is the slow step. So for this step, if I write the rate law, it will be rate equals to rate constant, concentration of A, whose coefficient is 1. So overall A to B is a complex reaction. But for a complex reaction, the individual steps, they will behave as elementary, right? So this A to P conversion is an elementary type reaction. So for A to B, I can say that rate constant, concentration of A, and the coefficient 1 here will be in the power, right? Now this is the rate law for the slower step, but the same rate law we can write for the overall reaction, right? So for this overall reaction also, rate law will be rate equals to rate constant into concentration of A, power 1, so order will be 1. You have to take care of only one thing here. From the slower step, when you write down the rate law, so whatever terms, whatever concentration terms you are taking here, right, those components should be present in the overall reaction. Like here I have just A, and A is also there in the overall reaction in the reactant side. So this is okay. But suppose from this lower step, I write down the rate law, and in that rate law, I have some unknown compounds, some unknown intermediates, which is not present in the overall reaction. So you need to remove that using equilibrium constant, just by expression. And don't worry, for complex reaction, how we calculate the order, we will understand that with help of an example, with help of an question. But I hope for elementary, you can directly find the order, right? And for complex, you need these steps. So let's see a question from this. All of you, please read the question carefully. And this is not a question. From this question, we are trying to understand how to get the order. But if you already know it, you know how to calculate order, right, of a complex reaction, you can pause the video, you can solve it by your own, and later on you can check the answer. So question is, mechanism of a hypothetical reaction x2 plus y2 gives 2xy. So here, this is your overall reaction. This is the reaction overall happening, right? It is x2 is a compound reacting with y2, and it is producing 2 moles of xy. This is your overall reaction. Now for this overall reaction, they have given these steps. Total we have 3 steps. 1, 2, 3. First step is fast, second step is slow, and again third step is fast. We have to find overall order of the reaction. But you know that to get order, we need the rate law. Now what I told you, out of all these steps, the slow step is known as rate determining step. So what we can do, from the slow step, from the rate determining step, we can write down its rate law expression. So for the second reaction, which is x plus y2 gives xy plus y, if I write down the rate law, I can say rate will be rate constant into concentration of the first reactant, which is x, whose coefficient is 1, so power 1, into concentration of the second reactant here, y2, power 1. So this is the rate law of the slower step. But what I told you, the rate law of slower step will be the rate law of overall reaction. But one thing we have to always take care of. Whatever terms we have here, it should be there in the overall reaction. Now if you check, y2 we have in the expression and y2 is there in the overall reaction. Very fine. Now here we have x. Now if you notice, in the overall reaction we do not have x. We have x2, we have xy in the reactant product side. But there is nothing like x in the reactant or product side. So that x is basically some intermediate species, right? So that x we need to eliminate from the rate law. And how that x will be eliminated? Using the equilibrium constant. Now in the faster steps, if you see the first step where x2 is dissociating into x plus x. Now for the first step, if I write down its equilibrium constant Kc. So for first step, equilibrium constant Kc will be concentration of x power 1 into concentration of x again power 1 divided by concentration of x2 power 1. I hope you all know very well that equilibrium constant is concentration of products divided by concentration of reactants raised to the power stoichiometric coefficient, right? Now from here, it is x power 1 into x power 1, that means x power 2, right? So x power 2 will be Kc into x2. X power 2 will be Kc into x2 power 1. Now from here, if you calculate the concentration of x, so that will be Kc into x2 square root. Square root can be written as power 1 by 2. So you need to substitute this here in the rate law. Now I can say that concentration of x can be written as Kc into concentration of x2 power half. Just substitute here. Instead of x, now this rate law can be written as rate constant into, instead of x I can write equilibrium constant into x2 whole power 1 by 2, and the remaining part is concentration of y2 power 1. Now rearrange k into Kc power half, I can separate it and I can write it like this, Kc power half, and later on you can multiply these two. Rate constant into Kc power half can be combined, right? And you can write a single constant for this into concentration of x2 power half into concentration of y2 power 1. So this is a constant. Now the concentration terms, if you look, we have x2 and y2, and x2 and y2 both are present in the overall reaction. So this is the rate law of your overall reaction. And now here if you notice, the order of x2 is half and order of y2 is 1. So overall order of the reaction will be 1 plus half, that means 1.5. So what should be the answer here? Definitely it should be A, which is 1.5. But my motive was not here to get the answer. My motive was to tell you how you can find the order in a complex reaction, right? From slow step, write the rate law, and then if any component is there which is not in the overall reaction, eliminate that with help of Kc of other reactions, right? So definitely in this case, answer will be A, that means 1.5. And now we have understood very well that how to get order for a complex reaction. And for elementary, you know what to do. The stoichiometric coefficients will be in the power, in the rate law for the concentration terms. Now students, we understood what is order very well, but we have one more term here which is called molecularity, right? So first we will try to understand what is the meaning of molecularity, and then we will compare the differences between order and molecularity, because from this topic you get some statement based questions. So first point is, what is molecularity? Molecularity is number of molecules participating in reaction in unit time and volume. Point is, whenever a reaction is going on, right? So during the course of reaction, the reactants will interact, right? In collision theory, you will learn that reactants will collide with each other. So reactants will interact or collide with each other. So in unit time, right, at one particular time, whatever number of reactants they are interacting, they are colliding with each other in order to give you the product. So those number of molecules, you call it as molecularity. Like for example, if a reaction is happening something like A2B2 reacting to give what? Twice of AB. So point is, at a time, if one molecule of A2 is there and at least one molecule of B2 is there, and these two molecules, if they collide, they can produce AB, right? So at a time, at least we should have two molecules here, one molecule of A and one molecule of B. So in this reaction, the molecularity will be 2. The molecularity will be 2. And molecularity can be simply calculated by, in the balanced reaction, adding this stoichiometric coefficient. This is a trick to find molecularity, right? The coefficient of A2 is 1 here, B2 is 1 here, so 1 plus 1 it is 2. But the meaning of molecularity is, at a time, one molecule of A2 is reacting with one molecule of B2. So number of molecule, count of number of molecules count is called as molecularity, which gives you the product. And order is a different thing. Order is experimental, right? We saw that order is related with your rate law. But point is, we have to see the difference between order and molecularity. So let's talk it separately once. What can be the possible difference we have between order and molecularity? So one of the difference will be their definition only, right? I'm not writing the definition part, but definition is also a difference here. Order is what? Order is the sum of the powers of the concentration term in the rate law. While what is molecularity? Molecularity is the number of molecules at a time colliding, right, to do the reaction, to produce the product, right? Another difference is the order. Just now you saw, we calculated order for complex reaction. So order can be calculated for both elementary and complex reaction. If you have elementary reaction, if you have a complex reaction, in both cases, you can calculate order. But you cannot calculate molecularity in case of complex reaction. If you have an elementary reaction, so for elementary reaction students, you can find the molecularity just by the stoichiometric coefficient. But if you have a complex reaction, so for complex reaction, you cannot find out the overall molecularity, never. Because for complex reaction, you have multiple steps, and in those multiple steps, different number of molecules will be reacting. So for molecularity, for overall reaction, in complex reaction, we cannot calculate. But order can be calculated for both elementary and complex. One more difference you can write between order and molecularity, and it is regarding their values. Students, molecularity is always integer, right? 1, 2, 3, 4, 5. Molecularity can never be fraction. It can't be 1.5, because if molecularity is 1.5, that means you have 1.5 molecule. So practically half molecule is not possible. So molecularity is always integer, like 1, 2, 3, 4, 5, 6, 7, 8, right? But order, it can have any value. It can be integer, it can be fraction, right? It can be 0, it can be positive, it can be negative. Order can have any value, 0, positive, negative, integer, fraction. So that is another difference we have between the order and molecularity. So at least these three differences between order and molecularity you should know. One is their definition, one is that complex reactions we can find order, but in complex reactions we can't find molecularity, and one is regarding the values. And now I hope you have understood pretty well that what is order, what is molecularity, and how they are different. They are completely different, right? One is related to your rate law, and one is related to your collision theory, the way the molecule reacts, right? Now, let's discuss some of the questions from these topics that we have done. Rate of appearance, rate of disappearance, rate laws, right? Order. So from these topics, let's see what type of problems we get in the examination. So we have the very first question. If you want to do by your own, please pause the video, solve by your own. Later on, check the answer. Question is, following data is for reaction between A and B, then the order with respect to A and B. Let me tell you, this is one of the most common question we have from the rate law. Yeah, this is a question of rate law first of all, and this is the most common. Even if you talk about your NCERT, so in NCERT, the back exercises, you have so many questions from this, where table will be made for different condition, rate and concentrations, data will be given, and using the rate law, you have to find out the order. So let me tell you how to solve these types of problem. First of all, the reaction is between A and B. So we can write down the generalized reaction here. The generalized reaction can be A reacts with B to give you some product, right? Now, we can also write down the general rate law expression, general, where we don't know the order. So the general rate law of this reaction can be written as rate is equals to rate constant into concentration of the first reactant A, power X, order, we don't know X right now, then concentration of the second reactant B to the power Y, right? So this is the rate law for our reaction. Now point is, they have given some data, right? They are saying that in the first experiment, when the concentration of A and B are 0.1, then your rate is this much, 2 into 10 power minus 3. Then in the second case, in another experiment, when the concentration of A and B are 0.2, so then rate is this, 4 into 10 power minus 3. And in the third experiment, when the concentration of A and B are 0.2, in that case the rate is 1.6 into 10 power minus 2. This data is always given in the question. Now what you have to do, you have to just substitute this data in the general rate law expression. Just substitute the values. Values of what? Rate, concentration. You don't know the rate constant and the order values. But if I substitute these three values, so I will get three expressions, I will get three equations, right? If I substitute the first value, so in first case rate is 2 into 10 power minus 3. So 2 into 10 power minus 3 will be equals to rate constant. In the first case, concentration of A is 0.1, B is 0.1. So 0.1 power X into 0.1 power Y. This is my first equation. Similarly, if I substitute the second data, I will get another equation. Here rate is 4 into 10 power minus 3. So 4 into 10 power minus 3 equals rate constant, and concentration of A is 0.2, B is 0.1. So 0.2 power X and 0.1 power Y. Now the third value. In third case, rate is 1.6. So 1.6 into 10 power minus 2 equals rate constant. In the third case, concentration of A is 0.2, B is 0.2. So 0.2 power X and 0.2 power Y. So from three data, we got three expressions just by substituting in the general rate law. Now what you have to do, you have to see the common bases, right? Like suppose in the first and second equation, the power is Y and the base of Y is 0.1. So if I divide 1 and 2, this Y term will be cancelled, and from here I can get the X value. So if you divide 1 with 2, so 2 into 10 power minus 3 upon 4 into 10 power minus 3, it will be 10 power minus 3 will be cancelled. 2 by 4 will be how much? 1 by 2 equals K by K will be cancelled. 0.1 by 0.2 whole power X, 0.1 by 0.2 whole power X, and this Y terms will be cancelled. Now from here you can easily say that 0.1 by 0.2 is nothing but 1 by 2, and if 1 by 2 power X is 1 by 2, so that means X is nothing but 1. right? So if you divide those two expressions in which y has a common base, you will calculate x. And if you do opposite, divide those two expressions in which the x has same base, so then you can calculate y. Like suppose if I divide the second equation with third one, so in second third the base of x is same 0.2. So in 2 by 3, if I do 2 by 3 here, so in second case in LHS we have 4 into 10 power minus 3, here we have 1.6 into 10 power minus 2. Okay, 1.6 into 10 power minus 2 can be written as 16 into 10 power minus 3. So it will be 4 upon 16. I hope you can do the calculation here, they are very easy. So 4 into 10 power minus 3 upon 1.6 into 10 power minus 2 will become 4 by 16 equals to, k and k will be cancelled out, here x power cancelled, 0.1 by 0.2 whole power y, 0.1 by 0.2 whole power y. Now here if you notice, this is nothing but 1 by 4 and this is 1 by 2 power y. So if 1 by 2 power y is 1 by 4, that means definitely here the power value y, it is nothing but 2. Y is what? 2. So that's how you have to solve the data problem. Write the general rate law, put the data, those many data that you have, those many equations you will get, and accordingly divide, you will get the order values. So here x is 1, y is 2. So overall order will be 1 plus 2, that means 3. And for A and B, the order is how much? 1 and 2. So in this case, answer should be C. Answer should be C. Definitely it is. Right? And I hope you have noticed one thing, that this particular question from this rate law we got in the NEET 2024 examination. And exactly the same question you can get in your examination, students. So you need to practice. You need to learn from the questions. And now I hope that these types of questions you can solve easily, right, by your own. Correct? And you need to practice the DPPs that we are providing in the description and on the PW app. So move ahead. Let's move ahead. Let's see more questions. Read this question carefully. It looks very simple. For a reaction which is 3A converting to 2B, the average rate of appearance of B is given by delta B by delta T. We know that, right? For product we call it rate of appearance and B is product here. So delta B by delta T is nothing but rate of appearance of B. Now the correct relation between average rate of appearance of B with average rate of disappearance. Okay, so you have to just make a relation between appearance and disappearance. You know how to do that. From the disappearance appearance, you calculate rate of reaction and just equate that. Like here, A is your reactant. So for A, minus of delta of A upon delta of T. For disappearance, we write minus here, right? Because it is decreasing. So minus delta A by delta T is the rate of disappearance of A, correct? And similarly, for B, they have already said that delta B by delta T, this is the average rate of appearance of B. They are not equal, they can be different. But when I divide that by stoichiometric coefficient, right, then it becomes equal and that is called rate of overall reaction. So for A, the coefficient is 3. So if I divide that by 3, now this becomes rate of reaction. And for B, the coefficient is 2. So if I divide this by 2, now this becomes rate of reaction. And both should be equal. Both should be equal. Right? So we have to find this delta B by delta T in terms of this delta A by delta T. So just take this 2 into LHS. It will come out minus 2 upon 3 delta of A by delta of T. And this should be equals to delta of B upon delta of T. Now what it means? It means that the rate of appearance of B is equals to 2 by 3 times of rate of disappearance of A. 2 by 3 times of rate of disappearance of A. So definitely in this case, your answer should be C, of course C. And this question we got in the NEET 2023 examination. So that's what I was telling you when I started about rate of appearance, rate of disappearance, right? So from that point also, that rate of reaction is equals to rate of appearance, disappearance divided by stoichiometric coefficient. From that topic also, you get questions in your NEET examination. right? But of course, these questions should look easy for you. You can do it easily in the examination. Let's move ahead. Let's see few more questions. Now this question is from rate law again. The correct options for the rate law that corresponds to overall first order reaction. Okay, this is a very simple question. 4 rate law expressions are given, right? And you have to answer in which case the overall order is 1, right? So you have the rate law, you have the power values of your concentration terms, just add them, right? Like in the first option, rate is rate constant into a power 0, b power 2. So here order will be 2 plus 0, that means 2. So this is not the answer because we have to get order 1. In the second case, a power 1, b power 1. So here order will be 1 plus 1, again 2. So this is not the answer. In the third case, a power half, b power 2. So half plus 2, it will become 2.5. Again, this is not the answer. So definitely answer will be the last one. A power minus 1 by 2 and b power 3 by 2. So minus 1 by 2 plus 3 by 2, if you do, it will come out 1, right? And we have to answer which one is of first order. So definitely in this case, option C, whatever rate law is there, in that case, the order is 1. So answer will be D, of course D. And this is one of the easiest question, and again we got it in NEET 2023 examination. So even if you have the knowledge regarding what is rate law and what is the meaning of rate law expression and what is the meaning of order in the rate law expression, so from that point also, from that basic point also, you get questions in the examination, right? Now another one. This is a very standard problem again from rate law. This is a very standard problem in which for a reaction, the rate law will be given and they will change the concentration or volume sometimes, 2 times, half times, 3 times, and then they will ask that what will be the effect on the rate of reaction, right? Like in this question, for a certain reaction, the rate is rate constant into concentration of a power 2, b power 1, right? When the initial concentration of A is tripled, now here you have to assume, suppose that initial concentration of A is X, initially let's say in first case. So finally, we are tripling it, we are making it 3x, from X to 3x, keeping the concentration of B constant. Now let's say that initially B is Y, so again it is Y. The initial rate would, okay, so we have to find the relation between rate. Assume that initially when it was xy, the rate was R1, and when it is 3x and y, now the rate is R2. Remember that data-based problem? In the same way you can solve this also. Now you have this two data, xy R1, 3xy R2, right? You have the rate law. Just substitute the data in the rate laws, you will get two equations. Divide that, you will get your answer just by dividing. If I substitute the first data, I can say that rate is R1 equals to rate constant K, concentration of A is X power 2, concentration of B is Y power 2. This I got by putting the first data. Now put the second data, right? Now the rate is R2, rate constant is same, concentration of A is 3x power 2, B is same, Y power 2. If I divide these two, I will get R1 upon R2 equals to, KK will be cancelled, right? X by 3x is 1 by 3, so 1 by 3 whole square, and this Y power 2 will be cancelled. So from here, if you notice, the R2 will become 3 into 3, 9 times of R1. And R1 was the initial rate, R2 is the final rate after tripling the concentration of A. So the final rate will be increased by 9 times, right? Increased by a factor of 9. Answer should be B. And again I am telling you, this is one of the most standard question we have from the application of rate law, right? So definitely in this case, for this question the answer is B, and this question again we got in NEET 2023 examination, right? So you can notice that every year we get 2 to 3 questions, right, from the chemical kinetics chapter, and those questions you can easily solve, especially if it is from the rate law part, Now one more question we have from the rate of appearance and disappearance point, but I want you to do this, all of you. Pause the video, solve first, then you can check the answer. A chemical reaction is given 4A plus 3B gives 6C plus 9D. The rate of formation of C is given 6 into 10 power minus 2 and rate of disappearance of A is also given. So for one of the reactant, rate of disappearance is mentioned, and for one of the product, rate of appearance is mentioned. So from these two or from any one, we can find the rate of reaction just by dividing by stoichiometric coefficient. Now, the rate of reaction. So first thing we have to calculate rate of reaction. Do that by the first one. Rate of formation of C is 6 into 10 power minus 2. The coefficient of C is how much? 6. So if I divide by 6, I will get rate of reaction. So rate of reaction, small r, is rate of appearance of C, which is 6 into 10 power minus 2 divided by stoichiometric coefficient, which is 6. So this will come out 10 power minus 2. Khatam. That's it. Right? Now we have to also find out how much amount of B is consumed in 10 seconds. Now, to calculate how much B is getting consumed in 10 seconds, you need to calculate what is the rate of disappearance of B, and that can be done by rate of reaction, right? This rate of reaction can be written as rate of disappearance of B, rate of disappearance of B divided by stoichiometric coefficient, and for B the coefficient is 3. So minus delta of B by delta T upon 3 should be your rate of reaction, which is 10 power minus 2. So from here I can say that B is disappearing by the rate of 3 into 10 power minus 2, and unit is mole per liter per second, or you can simply say molar per second, right? Now you can easily find, right? 3 into 10 power minus 2 molar per second means what? In 1 second, B is disappearing by the amount of 3 into 10 power minus 2 molar. So in 10 seconds, just multiply by 10. So in 10 seconds, right, how much B will disappear? It will be 10 into the rate of disappearance, which is 3 into 10 power minus 2, and it will come out 30 into 10 power minus 2. 30 into 10 power minus 2. So rate is 10 power minus 2 molar per second, and in 10 seconds it is 30 into 10 power minus 2 molar, it is disappearing. So in this case, 100% your answer should be B, and of course the answer is B. Answer is B, and this question again we got in the NEET 2022 examination. So till now you saw, right, that at least we have got 2 questions from the rate of appearance and disappearance relation, and that is very easy, right? Rate of reaction is appearance disappearance divided by stoichiometric coefficient. So now students, let's talk about the next topic, that is integrated rate laws. And let me tell you one thing, integrated rate laws we obtain from the general rate law, right, using integration for different orders. So let's understand bit by bit. Like let's say first we have an example, we have a sample reaction like this. So we have a reactant R. Now in a reaction it is converting into certain product. Done. Now be careful here, because we are considering that in our reaction we have only one reactant, and the coefficient, the stoichiometric coefficient here for us is 1. Now for this reaction, if I write down the general rate law expression, so rate law expression can be given as rate of reaction is equals to rate constant into concentration of the reactant, right, raised to the power x, and x is your order here. X can be 0, 1, 2, right, depending upon what is the order of reaction. Now the point is, we know very well that this rate can be written in terms of rate of disappearance of the reactant, right? So this overall rate of reaction, I can write it as rate of disappearance of the reactant R, and if the coefficient here is 1, then R can be written as minus of d of R upon dt. Minus of d of R upon dt is nothing but your instantaneous, right, rate of disappearance of reactant R. Now this will be equals to K, and see, instantaneous rate of disappearance here is directly equals to rate of reaction. Why? Because the coefficient is 1. If you change the coefficient like n, then here it will be minus dr by dt upon n. That will be the rate of reaction. So minus dr by dt equals to K into concentration of reactant R to the power order X. Now this equation, this particular equation is called as differential rate law. This is called differential rate law. Differential rate law. And this was your general rate law. Now point is, in any interval, if I solve this differential rate law by integrating it, right, of course, and for a specific order, so from that, by integrating whatever equation I get, that is called as integrated rate law. So one by one, we will see that for different orders. Like suppose if I have a reaction in which the order is 0. So if your order is 0, then the value of X will be 0 in that differential rate law. And this differential rate law, minus dr by dt equals to K R power X, here, if I put X as 0, so you know that R power 0 will be how much? 1. Right? So for 0 order, the differential rate law can be written as minus of dr by dt equals K and R power 0 will become 1. Now if you rearrange, you can rewrite it as minus d of R equals to K times of dt. And now if I integrate this for any interval for the course of reaction, like suppose I assume like this, that when initially time is 0 second, so at that time the initial concentration of reactant is R0, and after time t second the concentration of the reactant has become R. So for this interval, if I solve this, I can write it like minus of integration of initial concentration of reactant R0, final concentration of reactant R dr equals to K is your constant, integration of dt, and initial time was 0 second, final time was t second. If you solve this, I think this integration is very simple. You know that integration of d of x is x. So integration of d of r will be r, and if you put the upper and lower limit, so it will be r minus r0, but because we have a minus sign here, so finally you can rewrite it as r0 minus r, right? On the RHS, K, integration of dt will be t. If you put upper limit t minus lower limit 0, so t minus 0 will be t. So in the RHS it will be K into time. So this R0 minus R equals to KT. Students, this is nothing but your integrated rate law for your 0 order reaction. This is your integrated rate law for 0 order. So I hope that you will remember this R0 minus R equals to KT, and suppose sometimes if you don't directly remember this R0 minus R equals to KT, so within a minute you can find that by integrating from differential rate law. Now point is, okay, we got R0 minus R equals to KT as our integrated rate law equation. But what is the use of it? What is the use of this equation? So the use is, in a reaction, after any time t, you can find out what will be the concentration of your reactant if you know the initial concentration. In the equation itself, you notice that R0 is there. R0 is nothing but the initial concentration of reactant at the start of reaction, and R is the final concentration after time t. So for any 0 order reaction, if I have the data that what is the initial concentration, if I have the data that what is the rate constant, then after certain time t, what will be the remaining concentration of reactant R, that can be calculated. So this R0 is their initial concentration. Now this R is the concentration of reactant after time t. So at any time, after any time, you can find out easily from this equation that what will be the remaining amount of your reactant, right? And suppose from this graph, not graph, we are plotting graph. From this equation, suppose if you plot a graph between the concentration of reactant and time, you will notice that the equation in the graph part, it will be something like y equals to mx plus c. It will follow the equation y equals to mx plus c, right? where R is on y-axis, this is R naught, constant KT, time is on x-axis. So the graph will go like this. Now graphically, for the same equation, we can notice that with time, the concentration of reactant will decrease. And if it is zero order, then the decrement will be in straight line. Right? So I hope that you have noted down this graph also, and especially this integrated rate law. Now point is, just like zero order, the whole calculation here, it is about your zero order reaction. In the same way, just like zero order, we can also calculate for first order, second order, just by integrating it, right? Like after zero order, if I talk about our first order reaction. So for first order reaction, the x will be 1, right? I am taking that general differential equation here also. So according to that, minus dr by dt is equals to k, and for first order reaction, r power x will become r power 1. So you will have the concentration of reactant here. Now if you rearrange this, it can be written as minus of d of r upon r is equals to k times dt. And again, same type of integration. When your initial time is 0 second, so initial concentration is r naught, right? And after time t seconds, suppose that reactant has a final concentration of r. So in that interval, if I do the integration, here I will be getting integration of minus of d of r upon r, and here limit is initial concentration I am assuming r naught, final as r, equals k integration of dt, again initial time I am assuming as 0 second and final as t second. Now here students, I hope you know that integration of in general, right, 1 by x dx is natural log of x, ln of x. So similarly here, integration of dr by r will be ln of r, natural log of r. And when you put the limit, it will be ln of r minus ln of r naught, but we have a minus sign here, so it will interchange ln of r naught minus ln of r, ln of r naught minus ln of r. In the RHS part, it will be similar as zero order. K integration of dt is t, and if you put the limit t minus 0, it will be t. So kt. Now this expression looks quite similar to that of zero order, right? In zero order's integrated rate law, we had r naught minus r kt. So in the first order, we have ln of r naught minus ln of r equals to kt. You can rewrite this as ln of r naught upon r equals to kt. And this ln of r naught by r equals to kt, right, is nothing but your integrated rate law for first order reaction. And again, this equation can be interpreted graphically here also, right? In the zero order case, we plotted the graph between concentration and time, but instead of concentration, in case of first order reaction, what we do, we plot the graph between ln of r versus t. So if you are plotting ln of r versus t, you will look into this equation again, and ln of r will be equals to ln of r naught minus kt. So ln of r naught will be your intercept and minus k will be your slope. So again, for this case also, because I am plotting ln of r, the graph will be a straight line with negative slope. So with time, the value of ln r will decrease, and it will be strictly according to a straight line. So point is, in case of zero order, the graph between concentration and time is a straight line, and for first order, the graph of log of r versus time is a straight line. But again, this integrated rate law, this formula has the same use that I told you in case of zero order, right? From this formula also, what you can do for a first order reaction, if initial concentration is given, so after time t, you can find out what is the remaining concentration of reactant, right? So at initially the concentration is r naught, so after time t, the concentration of reactant is r here, right? So now I think you have understood the integrated rate law for zero order as well as first order. Now, With this integrated rate law, right, with the same topic, we have another point to discuss here, because this is connected with your integrated rate law, and that topic is half-life. Throughout the chapter, half-life is denoted by T half. So first let's understand what is the meaning of half-life. Students, half-life, I think from the name itself you can understand, right? Half-life means the time in which the initial concentration of reactant becomes half. Half-life is the time in which the initial concentration of reactant becomes half. What is the meaning of this statement? The time in which the initial concentration of a reactant becomes half. Suppose that in any reaction, if the initial concentration of your reactant is R0, so at the start of reaction at t equals to 0 second, the concentration of your reactant was R0, right? So the time in which it will become R0 by 2 from R. So this time interval is called as half-life. So if initially it is R0, so the time after which it will become R0 by 2, right? So that time interval is called as what? Half-life. Sometimes half-life we also say like this, that the time in which 50% of reaction completes. The time in which 50% of reaction is completed. Both has same meaning. When I say 50% of reaction has been completed, so that means 50% of the reactants amount has been reacted, right? So it will become R0 by 2. Now this is half-life. The meaning of half-life is very easy, but point is we have to do the calculation of half-life for different order. And also we have to establish a relation between half-life and the rate constant. The relation between half-life and rate constant is very important for you. Students, see, if I consider a zero order reaction, so in zero order reaction, just now you derived the integrated rate law, right? In case of zero order, the integrated rate law is R0 minus R equals KT. Now from this integrated rate law, we can easily evaluate its half-life. Suppose I take time as its half-life. So if I take time as half-life, then initial concentration will be R0, but the final concentration after one half-life will be half of the initial, that means R0 by 2. Now from here, R0 minus R0 by 2 will be R0 by 2. And if you calculate half-life from this, so half-life of zero order reaction will become R0 divided by 2 into K. So this is the, you can say, formula. This is a kind of formula we have for the half-life in case of zero order reaction. In zero order, half-life is initial concentration of the reactant divided by 2 times of rate constant. Now the same thing if you do for the first order reaction, you will get a little bit of different result. In case of first order, you know that the integrated rate law is KT equals ln of R0 by R. Now here in first order, if I take time as half-life, T half, so ln, you know that ln is natural log, means log base E. If I convert that into log base 10, so I will have to multiply by 2.303. So I convert this ln as log base 10, so it will be 2.303. Now log base 10, initial concentration R0, and after one half-life, the remaining concentration will be half of the initial. That means again R0 by 2. R0 by 2. So here if you calculate, R0 by R0 will be cancelled. This will be log 2. Log 2 value you should remember. I think you people should remember log 1, log 10, log 2, log 3. At least these 4 log values in this chapter you require. So log 2 is 0.3010. Log 3 is 0.477. Log 1 is 0. Log 10 is 1. So log 2 will be 0.3010, and if you multiply that with 2.303, roughly it will be 0.69. So from here, half-life of first order will be 0.69 approximately divided by rate constant. So in case of first order reaction, you can say that half-life is 0.69 divided by the rate constant. Now if you compare half-life in both the cases, so you will observe that in zero order reaction, half-life depends on the initial concentration of reactant, right? But in case of first order reaction, the half-life is independent of the initial concentration of reactant. So that means in case of first order reaction, the half-life remains constant, because K is constant, K depends only on temperature. So in first order reaction, half-life is constant. Now half-life is constant, that means what? Students, it means if you start from here, zero state. So suppose that when it is 100% completed, that means your reaction is over. So when your reaction is 50% completed, suppose that for 0 to 50% completion, the time required is T. So T will be your half-life. Now if you start from this 50%, so between 50 to 100, the half-life will be at 75. So from 50 to 75 also, it will require the same time, T second, because half-life is constant in first order. This is not the case in case of zero order, right? In zero order, half-life is variable, right? It depends on concentration, initial concentration of reactant. But in this case, for any half-life, right, the value will be same. So the time required for the completion of 50%, 0 to 50% will be same as the time required for 50 to 75%, will be same as the time required for 75 to 87.5 and so on, right? One more thing is there. Here we notice that in zero order, half-life is dependent on concentration. In first order, it is independent of concentration. So we should have a relation, a kind of proportionality relation between our half-life and the initial concentration with order. So you can note down a formula of this kind. In general, we can say, students, that half-life of any reaction is proportional to initial concentration of the reactant, right, raised to the power 1 minus n, where n is your order. N is your order, right? So if n is 0, right, 1 minus 0 is 1, that means half-life is directly proportional to R naught. We saw that, right? Directly proportional to R naught. If n is 1, right, so 1 minus 1, 0, R power 0 is 1. So in this case, half-life will be independent of concentration. We saw that in first order. And for second order, 1 minus 2 will be minus 1. So in that case, half-life will be inversely proportional to the initial concentration of reactant. Sometimes you get some of the numerical questions from this also. Yes, you know, from this what type of questions you can get? At one concentration, half-life is given. At another concentration, half-life is given. And from that, from this proportionality relation, you can calculate what order of the reaction. You can calculate order just by dividing half-life at C1 concentration upon half-life at C2 concentration equals to C1 by C2 whole power 1 minus n, where n is your order, right? So now I think you have understood half-life, and one of the main point here is in the question part, right? When we have to apply the integrated rate law, we need the value of rate constant. So in questions, what they do, instead of giving rate constant, sometimes they will give you half-life. So now it will be your task that from half-life, first you get the rate constant and then you apply the integrated rate law, right? So now as we have understood the integrated rate law, half-life, the dependency of half-life on the concentration, and how in case of first order reaction, the half-life remains constant, let's talk about a very, very, very interesting point that is related with your order. Students, in kinetics, we have some of the reactions which is called as pseudo first order reaction. Now, what is the meaning of pseudo first order reaction? Those reaction which theoretically looks of second order, third order, right? But experimentally, it behaves like a first order reaction, right? For example, You must have seen this reaction even in your class 10th also. If you take ester and you hydrolyze ester in a slightly acidic medium, so after hydrolysis, esters will give you carboxylic acid along with alcohol. Now here, theoretically, if you notice, we have two reactants whose coefficients are 1 and 1. So the molecularity or theoretical order of reaction will be 2, 1 plus 1. But experimentally, what we notice, the rate law for this particular reaction is something like rate constant into concentration of the ester, which is your first reactant, power 1, that's it. In the rate law expression, you will not find out water here. Why? Because for water, the concentration remains constant, right? You know, water has a molarity of 55.5. So that's a constant value. So point is, if a reactant is there whose concentration is constant, right? So that you can remove or that you can multiply with the rate constant itself. And in that case, the order or the dependency of reaction will be only on that reactant whose concentration fluctuates, whose concentration is variable. So theoretically, the hydrolysis of ester, right, it looks like a reaction of second order, 1 and 1. But experimentally, it follows first order, or the rate depends only on the concentration of one reactant, that is ester. So point is, in any reaction, if one of the reactant has a constant concentration, and one more point is there, if out of two reactant, for one of the reactant you have taken very excess amount, very high concentration. So in that case also, the change in that reactant whose concentration is high will be very low. So that can be removed from the rate law, because rate has no dependency on that reactant whose concentration is too high. So in those two cases, whether it is constant or whether it is too high, these theoretically second order reaction behaves as a first order reaction, and this is called as pseudo false first order reaction. You know that pseudo means false, right? So in general, this is called pseudo first order reaction. One more example of pseudo first order reaction you can take as hydrolysis of sugar, hydrolysis of sucrose. So sucrose, after hydrolysis, it gives you glucose and fructose, right? In that case also, the rate depends on concentration of sucrose but not on the concentration of water. So I hope that you have understood what is the meaning of pseudo first order reaction very well. Now, after understanding all the integrated rate laws and the order, let's discuss some of the questions from this topic, especially the integrated rate law. Let's see what type of questions we get in the examination. So you take your pen, paper and brain, try to do these questions along with me, all of you. I hope you can do it before me. I will be very happy then if you solve these questions right before me. So question is, if the rate constant for a reaction is 0.03 per second, now if you notice, they have given the rate constant, means K, which is 0.03, and please focus on the unit, per second. So if unit is per second, per hour, per minute, means it is a first order reaction. They don't need to tell it, we can easily identify. So the reaction is of first order. Now, how much time does it take for 7.2 molar concentration of the reactant to get reduced to 0.9 molar? So it is a direct question of integrated first law of zero order, right? They are asking the time in which the reactant's concentration will become 0.9 if it is initially 7.2. So directly apply the integrated rate law. You know it is Kt equals to now 2.303 log initial concentration of reactant upon final concentration of reactant. Now point is, rate constant they have given, and please focus on the unit part. Rate constant is 0.03. It is per second. So the time that you will be calculating, it will be in seconds only. So 0.03 into t equals to 2.303 log of initial concentration R0, it is 7.2, upon final concentration, which is 0.9, right? Now if you solve this, a simple log you need to solve. decimals you can remove, and 9 8s are 72, and log 8 you can calculate log 8 separately if you want. See, don't mess it up. Log 8, according to formula, it can be written as log 2 to the power 3. I hope so. 2 power 3 is 8. Now log m power n, power is taken out. So in log 2 power 3, I can take 3 outside. So it will be 3 into log 2. And log 2, they have given 0.301. So this will be 3 into 0.301. If you multiply, it will be 0.903. So the value of log 8, I got 0.903, and now I will use it here. So finally the time will be 2.303 into log 8 is 0.903 whole divided by 0.03. If you solve it further, approximately at least, so remove this decimal, multiply with 100 here. So this decimal will be removed, it will come here, 90.3. From 3 you can cancel it out, 3 3s are 9, 0.1. So this is 30.1, and 30.1 into 2.303, if you do approximately this multiplication, so 23 3s are 69. Definitely it will be 69 point something, right? Because the other options are very different, 210, 21, 23.1. So round off, our answer will be 69.3, and that should be the answer. Definitely 69.3. C is the correct option. And this question we got in the NEET 2025 examination, students. It's a very recent question, right? But I hope you have understood from integrated rate law what type of question you will be getting. Okay, in this question, they gave you the initial and final concentration, and they asked you to calculate the time. They can change it a little bit. Sometimes they can give you initial concentration and time. They can ask for the final concentration, right? Sometimes they can give you the time, initial and final concentration. They can ask you to calculate rate constant. So any type of calculation they can give, but every time you will have to use the same formula. And one more thing, out of 0 and first order, most of the time you will be getting questions from the first order reaction, right? Because 0 order becomes too easy. That's why they ask questions mostly from the first order reaction. Now let's see few more questions from this. Can you all do this with me? If you want to do it by your own, pause the video. Later on, just correct your answers, that whether you have done it wrong or right. Of course, you will do it correctly. You can't do mistakes in these types of questions now. So question is, if the half-life of a first order reaction is 1 minute, then the time required for 99.99% completion. Okay, first thing is, whenever you have these types of questions where percentage completion is given, assume always that initial concentration is 100. Like here, if I assume that initial concentration of reactant is 100. So after 99.9% of completion, the final concentration of reactant will be how much? 100 minus 99.9, that means 0.1. So this is my initial concentration 100, finally 0.1. Now half-life is given. Half-life is how much? Half-life is 1 minute. So from half-life we can easily calculate the rate constant, because rate constant is 0.693 upon half-life. So half-life is 1 minute, so this will be 0.693 per minute, right? Now just substitute the values, and you have to calculate what? You will have to calculate the time again. So K is 0.693 per minute into time equals to 2.303 into log base 10. Initial concentration is 100. Final concentration is 0.1. Now if you solve, I think here the calculation is very simple. Decimal you remove, it will be 1000. Log 1000 is log 10 power 3. So that will be 3 log 10. So log 1000 is basically 3. So here 0.693 into T equals to 2.303 into log 1000 is 3. So time will be 2.303 into 3 is something like 6.909. 2 3s are 6, okay. And this is 0.693. So not exactly, but nearly it is 10, because 0.69 into 10 is 6.9. So closest value we have to answer, right? So closest value here, it will be B, not 5, not 2, not 4, but it will be approximately 10 minutes. Right? It is a similar question, just like previous one. The only difference is here they have not given the rate constant directly, they have given the half-life. So from half-life we have to get the rate constant. So answer should be B, and of course it is. And again, even this question we got in the NEET 2025 examination. So you can see that same type of question we get, right, in the NEET examination again and again. Now let's do one more. Can you all solve this? But here you don't have to do the calculation, it's just a logical question. More precisely, graphical question, all of you. Question is, the given graph is representation of kinetics of a reaction. The y and x axis are for 0 and first order reaction, okay, respectively. Okay, so what they are asking, they have given you a graph, right? This is your y axis, okay. This is your y-axis, this is your x-axis, and the graph, the plot between y and x is a straight line parallel to x-axis. So this type of graph you get when something is constant, right? If something is constant with respect to x, if something is not changing with respect to x, then only you get this type of graph. Now you have to decide, if it is 0 order and first order, what will be the parameters on y and x-axis, right? Like for example, here the first option is, in 0 order, if I take concentration on y-axis and time on x-axis. So if I take concentration and time, so for concentration time, in case of 0 order, we know that concentration of reactant will decrease with time. It should not be constant. So definitely first can't be your answer. In second case, again y concentration time, this is again not possible, because whether it is 0 order, whether it is first order, right, in both the cases the concentration will decrease with respect to time for reactant, and it is a general point, right? I told you at the start, for any forward reaction with time the concentration of reactant should decrease. Now in the third case, for 0 order, they are saying if I take rate and here concentration, yeah, this is correct, because in 0 order rate remains constant, rate is independent of the concentration of reactant. So if I take concentration of reactant on x-axis, rate on y-axis, then for 0 order it will give you a straight line, right? And for first order, if I take half-life on the y-axis and concentration on x-axis, this is also correct. We saw that in case of 0 order, half-life depends on concentration of reactant, but in first order the half-life, right, remains constant. So if I take for first order half-life on y-axis and concentration on x-axis, so it should be constant, because half-life of first order is independent of concentration of reactant. So no doubt in this case the answer will be C. We don't have to check the next option. Yeah, C. Although in the D option, if you notice, so for 0 order, if you take rate on y-axis and concentration on x-axis, so this is correct. But for first order, if you take rate and half-life, rate versus half-life, so it can't be constant, right? That's why here option D is not possible. Now, I hope that you have understood from these many questions that what type of question you can get in your exam from this integrated rate law and half-life part, right? But let's see one more question again from the first order integrated rate law only, and this you can do very easily. Question is, the rate constant for a first order reaction is this much. So rate constant is given 4.6 into 10 power minus 3 per second. The time required to reduce 2 gram, 2.2 gram. Same question. Apply KT equals to 2.303 log R naught by R. So here K is how much? 4.606 into 10 power minus 3. Time we have to find out. equals to 2.303 into log initial. Okay, see, notice here they have given the amount in gram, right? But we take the concentration value. But point is, for same compound, the ratio of gram and molarity will be same because they have the same molar mass, they are in the same container. So instead of concentration ratio, we can directly use mass ratio here. So it will be 2 upon 0.2. And the calculation is too easy here. Can you notice, all of you? 0.2 will be cancelling 2 by 10 times, log 10 is 1. So T will be directly 2.303 upon this 4.606 into 10 power minus 3. So this 10 power minus 3 you can take in numerator, it will become plus 10 power 3, and this is cancelling 2 times. 10 power 3 is 1000, so it is 1000 divided by 2, so it is 500. And the unit of rate constant was per second, so this will be in seconds. Answer will be 500 seconds, right? So almost 3 questions we did of similar kind from this integrated rate law of the first order. And of course here answer will be B, and this question we got again in NEET 2020. So same question we had in 2025, right? Just like this NEET 2020 question. So now students, I hope that we have understood that how concentration affects the rate of reaction. Basically, whatever topics you discussed till now, like rate law, integrated rate law, right, order, everything. So all those topics just was a part, they were a part of how concentration affects your rate, right? Now let's talk about that how the rate of reaction is affected by temperature. So first thing is in general, temperature increases the rate of reaction. In general, temperature increases the rate of reaction, right? But obviously, it will also depend on whether your reaction is exothermic or endothermic, right? Because if it is endothermic reaction, then in that case, definitely, if you increase temperature, the rate of reaction will increase. But in the case of exothermic reaction, if you increase the temperature, the rate can also decrease. But point is, if you talk about the initial phase of the reaction, at the start of reaction, so at the start of reaction, for any reaction, the temperature will increase the rate. The temperature will increase the rate. Now, we don't have, it's not like that we have only logical explanation for this. We have so many mathematical things to relate temperature and the rate of reaction. But the very first thing you should know here is, and sometimes you get questions from this also, the very first thing that you should know is, by every 10 degree rise in temperature, rate of reaction almost becomes double. So this is one of the experimental points we have, that for any reaction, when we increase the temperature by 10 degree, so rate approximately doubles. Rate approximately becomes 2 times. But it is again approx value. The actual range it is from 2 to 3. It can be 2 times, it can be 2.2 times, it can be 2.5 times, it can be 3 times. But most of the time it is close to 2. Right? So by every rise of 10 degree in the temperature, the rate of reaction becomes double. And overall, in general, what you can say that when we increase temperature, the rate of reaction increases, right? Now, to relate this temperature with rate and rate constant, we have a very famous equation known as Arrhenius equation, right? The equation is given something like rate constant K, it is equals to A times of e to the power minus EA upon RT. Now here you need to understand these terms very well. So first term is rate constant. You know very well, you saw that rate constant in the rate law expression, and you know very well that rate constant is directly proportional to the rate of reaction. If a reaction has more rate constant, that means its rate will be higher, correct? A is Arrhenius constant, or it is also called as a pre-exponential factor because it is multiplied before this e to the power minus Ea by RT. So A is Arrhenius constant, or sometimes it is also called as pre-exponential factor, pre-exponential factor. I will tell you very soon that what is the exact meaning of A. But now let's talk about e to the power minus Ea by RT. Now here R and T you know very well. R is your gas constant. In joules it is 8.314 joule per Kelvin per mole. T is your temperature, absolute temperature in Kelvin. Ea is a new term for us. Ea is called as activation energy, and we have to deal with this in detail. Activation energy is a separate topic for us. Activation energy is a separate topic for us. But point is, K equals to A times e to the power minus Ea by RT is known as your Arrhenius equation, where Ea is activation energy, and activation energy is nothing but the minimum amount of energy required to start a reaction, to initiate a reaction, right? So we will come to that, we will talk about activation energy, but first let's see this formula. Now this formula, this Arrhenius equation, K equals to A to the power A into e to the power minus Ea by RT, you can express that into log form as well. You can express this formula in log form as well. How? Just take natural log on both sides. If you take natural log, so the LHS here, it will become natural log of K equals to ln of A into e to the power minus Ea upon RT. Now point is, if you know that log, if you talk about the formulas in log, so log m into n, inside the log if you have two numbers in the multiplication, log m into n, so that you can write it as log m plus log n, right? So here I can say that ln of K, natural log of K will be, this ln of A into this can be rewritten as ln of A plus ln of e to the power minus Ea by RT. And again, from ln e to the power, this power can be taken out and ln of e will be 1. Log base 10, 10 is 1. So similarly, log base e is 1. So ln of K equals to ln of A, and this will be minus Ea by RT. And if you convert this natural log into log base 10, so you will have to multiply with 2.303 here and here. So if I divide the whole equation by 2.303, then I can write it as log K equals log A minus Ea upon 2.303 RT. Now, log K equals log A minus Ea by 2.303 RT. This is also Arrhenius equation. And K equals to A into e to the power minus Ea by RT. This is also Arrhenius equation. Only the forms are different. This is in exponential form and this is in log form. According to question, you will have to use. According to question, you will have to use either this formula or this formula. But again, you will be getting numerical questions from this. You will be getting numerical questions from this. Log K, log A minus Ea upon 2.303 RT. And from this, the most famous question is, they will give you the value of K at two different temperatures and you will have to calculate Ea. You will have to calculate what? Ea. Right? That's the most standard question we have from this Arrhenius equation. But again, from Arrhenius equation, you can get graphical questions also. Students, just remember this formula. Right? If I take this, log K equals log A minus Ea upon 2.303 RT, and I try to plot a graph from the equation itself, a graph between log K and 1 upon time, 1 upon temperature, not time. If I plot a graph between log K and 1 upon temperature, so you can notice, if you compare, I am putting log K on y-axis, 1 upon T on x-axis. So this minus Ea by 2.303 R will be your slope and log A will be your intercept. Again, the slope is negative. So the plot of log K versus 1 by T will be a straight line with negative slope, something like this, right? Where this intercept value is nothing but log A, and the slope of this curve, not curve, straight line, the slope of the straight line will be minus EA upon 2.303 R. You know, sometimes what will happen? They will give you this graphical questions also. Like they can ask for a reaction, right? The slope is given, slope will be given to you, and you will have to find out the EA value. So how you can do that? Just multiply slope with 2.303 R, you will get the activation energy of your reaction, right? Now, let's talk about a little bit onto this activation energy and of course their graph, and then we will see questions of the Arrhenius equation also, what type of questions we get from the Arrhenius equation. But first let's talk about activation energy, which just now I told you denoted by EA. EA. Now, it is defined as the minimum amount of energy required to start or initiate a reaction, start a chemical reaction, right? So point is, to start any chemical reaction, right, to convert reactant into product, first always you need to give some energy to the reactant, or you can say like this, initially in any reaction, first the reactants, they will absorb certain amount of energy. Now when they have a sufficient amount of energy, which is called threshold energy, I will tell you that in the graph part, right? So when those reactants, they achieve certain amount of energy, the threshold energy, then only they starts converting into the product. So the minimum amount of energy required to start the reaction, to start the conversion of reactant into product, is called as activation energy. Like suppose if I have a reaction like this, R is my reactant, P is the product. So this reaction is happening. Now in this reaction, of course every compound, they have certain amount of energy, every compound they have certain amount of energy. So initially the reactant that you have, it will have certain amount of energy. Let us say on y-axis here I am plotting energy. So this is the energy of reactant, right? But this amount of energy is not sufficient to convert into product. So what I will do? I will supply energy to the reactants, and the energy of reactants, then it will increase. The energy of reactant, it will increase. And at certain point, it will start converting into product, right? And when product formation will takes place, right? As the product is getting formed, the system will start releasing energy. So then your energy will decrease again, like this. And finally, this is the energy of your product that you are getting. This is the energy of your product, right? So in this case, the reactant's energy was this, and reaction started at this point. So this is the amount of energy that reactant requires for the reaction. So this is nothing but your activation energy. Now one more thing, the energy of reactant and activation energy, if you add these two, so the total energy of the reactant we have here, this is called your threshold energy. This is called your threshold energy. And at this point, when your energy is highest, right, then you don't have reactant or product. At this point, the composition is called as activated complex. Activated complex. It's not reactant or product. It's something in between. Activated complex. Correct? And finally, this is your energy of product. Now, few points you need to observe from the graph of activation energy. Please focus here. In this graph, if you notice, so as compared to energy of reactant, the product has low energy. As compared to energy of reactant, the product has low energy. That means overall this reaction will release energy. This is exothermic reaction. This is exothermic reaction. So from this graph of activation energy, you can easily predict that whether your reaction is exothermic or endothermic. In this case, the reaction is exothermic. Why? Because energy of reactant is more than energy of product according to graph. Suppose that for any other reaction, in the graph if you notice that energy of product is more than energy of reactant. So you can easily say that it is an endothermic reaction, right? So from graph you can predict that. Not only that, it's exothermic, no doubt in that, but we can also calculate from the graph itself that what is the enthalpy change for this particular reaction. Students, whatever difference you have between the energy of reactant and energy of product, so this difference between energy of reactant and product is nothing but your enthalpy change for the reaction, right? Or from here I can say that delta H graphically from this can be calculated as energy of product minus energy of reactant, and because energy of product is less, in this case delta H will be negative, and you know very well that in exothermic reaction the sign of delta H is negative, and for endothermic the sign of delta H is positive, right? So activation energy is very simple, even its graph is also simple, but its graph has so many interpretation, and that's why you get so many graphical questions from this activation energy, right? So this was the introduction of activation energy, that what is activation energy and how we plot its graph or its energy profile. Now let me tell you few more points regarding your activation energy. Students, can you see this? For any reaction, I plotted the graph of activation energy, and suppose I got this kind of graph. Of course, I don't need to tell you now that this is energy of reactant, this is energy of product, right? Okay, let me write it here, reactant, product. Again, if you notice, product has less energy than reactant, so it is overall exothermic reaction. But if you notice, in this graph we have two maxima points. So that indicates number of steps in a reaction, right? If the graph of activation energy, it has only one maxima, that means this reaction has only one step. That means it is a elementary reaction, right? But if your reaction, it has two maximas, that means this is having two steps, step 1, step 2, right? In step 1, it is going from here to here. In step 2, it is going from here to final product, right? So number of maxima gives you the number of steps in the reaction. Not only that, now this reaction, as it has two steps, I can say that it is a complex reaction. It is a complex reaction. Also, from this graph, we can find out the slow step. Remember, slow step, RDS, rate determining step, right? Here if you notice graphically, we don't have much difference here, but let's assume that in the second step, the activation energy is more. In second step, we require more energy as compared to the first step, right? So the step where activation energy is more, that will be the slow one, because that step requires more energy to start. So in this case, the step 2 will be the RDS or slow step. Let me write it for you. Let me write it down for you. The step whose activation energy is more is slowest step or RDS step. So from graph we can find delta H, we can find whether reaction is exothermic, endothermic, we can find whether the reaction is elementary or complex, we can also find that which step is RDS or slow step. So these are the uses of the graph of activation energy. Right now, I hope that you have understood Arrhenius equation as well as the activation energy very well. Now let me tell you one more point here. You saw that in Arrhenius equation, K is equals to A times e to the power minus EA upon RT, right? This is the Arrhenius equation. Now if you focus on the Arrhenius constant, this A value, students, A is nothing but the maximum value of rate constant. According to this equation, it is clear that if I increase temperature, so then rate constant will increase. By increase in temperature, the rate constant will increase, right? So if I take temperature as infinity, so infinity will be the highest temperature, highest possible temperature, maximum temperature. So theoretically, if you put temperature infinity here, EA by infinity will become 0, e to the power will become 1, e to the power 0 will become 1, and at t equals to infinity, you will be getting k equals to A. So that means what? At maximum temperature, at very, very high temperature, practically infinity is not possible, so we can say that at maximum temperature, at very high temperature, rate constant becomes equals to Arrhenius constant. So I can say here that Arrhenius constant is nothing but the maximum value of rate constant. Arrhenius constant is nothing but the maximum value of rate constant. At very, very high temperature, Arrhenius constant is the rate constant. So I hope that this point is clear to you. What is the exact meaning of your Arrhenius constant? And now you know EA and RT very well. So let's see one more point, because again it is related with your activation energy only. So point is, you know from your childhood that a catalyst increases the rate of reaction. A catalyst increases, and we have inhibitors which will decrease the rate of reaction, but catalyst will increase the rate of reaction. But point is, how catalyst increases the rate of reaction? That's the question. So answer is by decreasing the activation energy. Catalyst increases the rate by lowering the activation energy, the energy required. Correct? So graphically, if I explain this to you, please focus here. So this is, let us say, energy of reactant. This is your energy of product. This time I have taken endothermic reaction. Now suppose that a reaction is happening, right, without the presence of catalyst. So without catalyst, its pathway is like this. So this is your activation energy without catalyst. Now the same reaction, if it happens in the presence of a suitable catalyst, its energy pathway will change. It will be something like this. Now we require less amount of energy, right? So this I can say without catalyst, and this I can say with catalyst. So from graph itself it is clear that in any reaction with suitable catalyst, we require less energy to start the reaction, and that's why the rate of reaction is more. And without catalyst, we require more energy to start the reaction. So that's why without catalyst, the rate of reaction will be less. So overall point is, a catalyst will increase the rate of reaction by lowering its activation energy, So now students, from this Arrhenius equation part and the activation energy part, let's see some of the questions, right? You can also try this along with me. Pause this video, solve by your own first, then only you should match the answer. So first question is, which of the following plot represents the variation of ln of k, natural log of rate constant, versus 1 by temperature in accordance with Arrhenius equation, So just a graph and its plot, and I have already told you, right, the graph between log k and 1 by t. So similarly you can plot between ln of k and 1 by t, right? You know that ln of k mathematically it is equals to ln of a minus ea upon rt. So from this mathematical equation, if I plot ln of k on the y-axis, and 1 by temperature on the x-axis, so minus ea by r will be your slope and ln of a will be your intercept. So overall it should be straight line, right, with negative slope, and the only graph is here, is the third one, in which the graph is a straight line. So this is your intercept ln of a, and the slope is decreasing. Okay, negative slope means the graph will be in decreasing order, right? Mathematically, graphically. And positive slope means the graph, the straight line will be in increasing order. So the graph in 1, 2, 4, they have positive slope, and only in the third graph the slope is negative. So in this case, definitely the answer will be third one. And students, this question we got in the NEET 2024 examination, right? So along with each and every session, what I'm trying to do, I am trying to include more and more PYQs, right? So you can understand what types of question you get in the NEET examination. Let's see one more. Rate constant for a reaction at 500 and 700 Kelvin are 0.04 and 0.14 per second respectively. Find the activation energy. So this is the question I was talking about. This is the most you can say standard question you have, right, from the Arrhenius equation. Now Arrhenius equation in general you write it as log K equals log A minus EA by 2.303 RT. But in these types of question, you can use this formula. You can take log K2 upon K1 equals to EA upon 2.303 R into 1 upon T1 minus 1 upon T2, right? So K2 is the rate constant at T2 temperature and K1 is the rate constant at T1 temperature, and R, you know, it is 8.31 joules per Kelvin per mole. Now in this question, if you notice, right, they have given everything. Log, let us say that 500 Kelvin is T1 and 700 is T2. So automatically 0.04 will be your K1 and 0.14 will be your K2. So here K2 is 0.14, right, upon K1 is 0.04 is equals to EA upon 2.303. You can put the value of R later on. So R 1 upon T1, T1 is 500 minus 1 upon T2, which is 700. And I hope that easily you can calculate the EA from this, right? A little bit of calculation and you will be getting your answer. Let me do a little bit for you. So decimal will be cancelled out, and 14 by 4 you can cancel out as 4 3s are 12.5. So this is log 3.5, and that's why in the question they have given log 3.5 as 0.5441. So directly this log 3.5 I can take it as 0.5441 is equals to EA upon 2.303. The value of R now you can put it is 8.31, and EA you will be getting in joules into this 500 and 700. This will have a LCM of 7 5s are 35. 3500 upon 500 is 7 minus 5. Now you can easily do the calculation, right? Just multiplication division you have to do. From here your activation energy will be 0.5441 into 2.303 into 8.314 into 3500 divided by 7 minus 5, that is 2. And if you calculate that, you will get your answer as option C, right? But point is, if this type of question is given in which at two temperatures, right, their rate constants are given and you have to calculate the activation energy, you can use this formula directly, right? Log K2 by K1 EA upon 2.303 R 1 by T1 minus 1 by T2. And this question again we got in the NEET 2024 examination, right? Let's see a few more questions from this temperature dependency of rate. We have a logical question here. Question is, activation energy of a chemical reaction can be calculated if one knows the value of, okay, for the same topic we have done a question, right? Activation energy can be calculated if rate constants at two different temperatures are known. Just now we solved the numerical, right? If T1, T2, K1, K2 is given, we can find the activation energy. So for this question, definitely the answer will be D. And again, this question we got in NEET 2024. So in NEET 2024 only, we got two similar type of question from this chemical kinetics. Now the next one, again we have a statement based question. a reaction can have zero activation energy. See, experimentally, it is not possible that a reaction will have a zero activation energy, because if you want to do a reaction, to start a reaction, right, it always requires a certain amount of energy. So activation energy of any reaction can never be zero. And they are saying that a reaction can have zero. So assertion is false here. This statement itself is false. Now reason is, the minimum extra amount of energy absorbed by reactant molecule so that their energy becomes equal to threshold value is called activation energy. Just now you have seen the definition of activation energy, and in reason they have just written the statement of definition of activation energy, which is absolutely fine. The minimum energy required to initiate a reaction or to raise the energy to threshold value is called as activation energy. So here reason is absolutely correct, true. Now let's check the option. The option in which A is false, R is true will be the correct option. So definitely in this case again answer is C. A is false, R is true. Yes, A is false, R is true. And this question again from the activation energy part we got in the NEET 2023 examination. Now one more a similar type of question. The slope of Arrhenius plot between ln of K versus 1 by T of first order reaction is this much. Okay, I was telling you, right, that graphically they can give you questions like where slope will be given and you will have to calculate the activation energy. Same question is there, right? So you know that when you write down the equation of ln of K and 1 by T, the equation is something like this, right? Ln of K equals to ln of A minus EA by RT. And if you plot this on y-axis, 1 by temperature on x-axis, then minus EA by R is your slope, right? And that slope in this question, it is given as minus 5 into 10 power 3. So I can directly say that slope is minus 5 into 10 power 3. And this should be equals to what? Minus of EA upon R. And the value of R, you know, it is 8.314. If you multiply these two, you will get your EA value. And round off if you do, it should be something 8 5s are 40, 41 something. It should be B. It should be B. Definitely B. And this question we got in NEET again 2023. But see, this is a very, very easy question, right? If you know the equation, if you know how we plot the graph, if you know the meaning of slope and intercept, right? So they have given you the slope, and according to this equation, slope is EA by R. Just equate those two and you can find out the activation energy. So activation energy can be calculated from graph also and by the value of rate constants at two different temperature also, right? Of course, answer is B, 41.5 kilojoules. Now students, after all these topics, after especially understanding the dependency of rate with concentration and temperature, we have one more topic, and from this you will never get numerical type problems because you will be always getting conceptual problems from this. But we have an approach of explaining chemical reaction, and that approach is called collision theory. You know collision theory, what it says? It says overall that a reaction will happen due to the collision between the reactant molecules. So in collision theory, what we do, basically we connect, right? We relate the rate of reaction with the collision of reactant. Overall, you can say that more the collision of reactant molecules you have, right, more is the rate of reaction. More collision, more rate. But before relating collision with rate, we have created few terms here, and those terms you need to understand first. Like a term is here which is called collision frequency. Collision frequency, right, denoted by Z. Collision frequency basically tells you regarding the number of collision. Collision frequency is number of collisions per unit volume per unit time. Per unit volume per unit time. And now because we have created a parameter here for number of collision frequency, right? So Z is what? Z is basically number of collision. And what collision theory suggests? It suggests that rate is proportional to the collision frequency. Somewhere rate is proportional to the collision frequency, right? But if you want to know the exact relation between rate of reaction and collision frequency, so the exact relation between rate of reaction and collision frequency is rate of reaction is equals to, please focus here because we have terms here and that we need to understand very well. So rate of reaction is equals to collision frequency Z into a factor P, and this P or this factor is called as steric factor or probability factor. This factor is called as steric factor or probability factor, right? So rate of reaction equals to collision frequency into steric factor into e to the power minus Ea upon RT. This is the same term that you saw in the Arrhenius equation, e to the power minus Ea by RT, where Ea is your activation energy and T is the temperature of the reaction. Now this is a complete formula we have for the collision frequency and rate. Now rate and collision frequency you have understood, right? Z is collision frequency, that means number of collision. Now this term P, students, steric factor, it tells you regarding the orientation of molecules, right? How perfectly the molecules are oriented so that they can have effective collision, so that after collision they can give you the product, right? So whether the orientation is perfect or not for the molecules, that term we explain by steric factor, right? And again, this whole term, although we have a combination of terms in this EART, but still this whole term e to the power minus Ea by RT, it has a very big name, right? You know, e to the power minus Ea by RT is called as fraction of molecules having sufficient energy for reaction. Having sufficient energy, right, for reaction. So suppose that in your reactant side, for example, you took 100 molecules. Total you have 100 molecules in the reactant side. Out of those 100 molecules, right, if 70 molecules have enough energy so that they can give you the product, right? So out of 100, if 70 molecules have the sufficient energy to react, so there the fraction of molecule having sufficient energy will be 70 by 100, that means 0.7. So this whole term is a fraction. The value of e to the power minus Ea by RT will lie between 0 to 1, between 0 to 1, and it depends on temperature. It depends on temperature, right? So this is a fraction of molecule. This is your steric factor, or it depends on orientation. This is your number of collision. Now in this formula, you will not be getting any numerical, but the terms are important. You will be getting questions from the terms itself. Now let's try to understand this fraction of molecules having sufficient energy with help of a graph. Students, can you notice this? We have a graph here, and in this graph what we are doing, on the y-axis we are plotting fraction of molecules, or for understanding purpose you can say simply number of molecules, right? So fraction of molecules or number of molecules. On the x-axis we are plotting kinetic energy or speed or velocity. Now point is, if you notice this curve, so within this curve, if I draw multiple points, so these points indicates number of molecules, or more precisely, within this curve, whatever area you have, so that area indicates number of molecules. That area indicates number of molecules, right? Now here, if you notice, if I go from left to right on the x-axis, the energy will increase, and this is the energy value, you can say, after which you can say reaction is happening. After which reaction is happening. So if a molecule has energy less than this, right, then it will not react. But if a molecule has energy more than this, so then it can convert into product, right? So here in this graph, in this region, you can notice this is the area, or this is the number of molecule which have sufficient energy. So this part here will indicate your e to the power minus E by RT. This is the fraction of molecules which have sufficient energy for reaction, right? And this area or this e to the power minus E by RT term will increase with temperature. Like when you increase temperature, like we have a second graph here, if you notice, in which the plot is given at two temperature T1 and T2, and T2 is more. So when you increase the temperature, the maxima will go down, right? But on this region you will notice that the curve will move upward. Upward means at lower temperature, these are the molecules, or this is the region which have sufficient energy. But when you increase temperature, right, now you can say that these are the fraction of molecules which have sufficient energy. So with increase in temperature, the maxima will go down, but this area will increase. The fraction of molecules having sufficient energy for reaction will increase. And now I can say graphically that this region, which I called fraction of molecules having sufficient energy, this region I can relate as it is e to the power minus EA by RT. Right? And the range of e to the power minus EA by RT will be between 0 to 1 because it is a fractional term. And you know that any fractional term, it can have value between 0 to 1. Right? So this is the point of your collision theory. Right? In collision theory, this formula is very important for you. Right? Rate equals to frequency into steric factor into fraction of molecules having sufficient energy. Then this graph is important for you. You need to have understanding of this graph, that in this curve, right, the area here indicates number of molecules, and after this, whatever molecule, whatever area you have, that indicates those molecules which have sufficient energy for the reaction. Now let's quickly see a question from this collision theory. Can you solve it before me? Pause the video, you can give your answer, and later on you can confirm that. So question is, an increase in the concentration of reactant of reaction leads to change in. So when we increase concentration, so if you increase concentration means what? Basically you are increasing number of particles, number of molecules. Now if number of particles, right, number of atom molecules will increase, so by that activation energy can't increase, heat of reaction will not increase, threshold energy will not change, but collision frequency definitely it will increase, right? More concentration means more number of particles, and in a container if I have more number of particles, then definitely I will have more and more collision in unit time, right? So more collision means what? Collision frequency. So of course answer is D here, and this question we got in NEET 2020 examination. But point is, we started this chapter by saying that increasing the concentration will increase the rate of reaction. And now we are understanding that point with help of collision theory, that how increasing concentration increases the rate of reaction, due to increase in the collision frequency, due to increase in the number of molecules, number of atoms, number of particles, right? So overall, in this chemical kinetics chapter, you need to know, you get 2 questions in the NEET examination, and that you can solve easily. And if I summarize, overall I can say that most of the time you get questions from the rate law part, whether it is order calculation or whether it is that data based problem, or whether those types of questions in which you increase the concentration or volume of certain reactant, then what is the effect on rate. So those types of questions you get from rate law. After rate law, right, you will be getting questions from integrated rate law, and again from integrated rate law the question will be mostly numerical. Then from the Arrhenius equation, you can get numerical as well as conceptual problem. And then the last one, collision theory. From collision theory you won't get numerical questions, mostly you will be getting statement based, right, conceptual logical questions, right? So I hope that after watching this session, right, each and every topic of chemical kinetics now you can solve, right? So now in homework, what is your task? you need to download the DPP, the practice sheet, in the video description, or you can get that on the PW app also. And after watching this session, please complete all the questions that we are providing in the DPPs, right? Because if you complete all those questions, believe me, right, that means you are practicing each and every type of question. And once you are done with that, once you have done each and every type of questions, then you can solve questions of the examination very easily. Correct? So thank you so much. Now we will meet in the next video. Bye bye, over and out.